Hello everyone, my name is Lila Serrahis and I'm a postdoctoral associate at NYUAD. I'll be giving a short introductory presentation to the exciting field of graph neural networks and how we have used it for hardware security. So the motivation why we study graphs is that circuits can naturally lend themselves to graph representations. You can see the circuit here on the left, it is nicely captured as a graph on the right. Gates are connected by wires in the circuit, and these are represented as nodes and edges in the graph. So once we have the circuit represented as a graph, now we can ask ourselves some interesting questions about the circuit, whether the circuit contains malicious hardware, for example, or not. When learning on the graph, we will need to do feature engineering. We want to take the network and represent the nodes by a set of features and obtain a set of structured data. Then we can apply some learning algorithm and build a model to solve for a specific task. And we like to skip the step of feature engineering and automatically represent the circuit by an embedding that captures its properties, which can then be passed to the downstream task. So this is an example. We would have a network and we wish to obtain an embedding vector for each node in this graph that will capture its properties. And this is helpful for different types of networks. It is used in protein-to-protein interaction graphs and in social networks in addition to circuits. Now, to implement this task-independent embedding generation, we use graph neural networks, GNNs. And in a GNN, to get the embedding of a node, we will start with its own features, and then the node will get information from its neighbors, where its neighbors obtained information from their neighbors. So at the end, we will get an embedding for each node that will capture its properties, the properties of its neighbors, and the structure of the graph. So we started with a network and a feature matrix where each node in this network was associated with a feature vector that captures its initial properties. These were fed to the GNN, and the GNN was able to construct an embedding matrix that can be used for different classification tasks. So we can use the generated embeddings for node classification tasks, for subgraph classification tasks, or link prediction. So for node classification, we are interested in the properties of the nodes themselves. And in subgraph or graph classification, we are interested in the properties of all of the nodes in the subgraph in the graph. So we're looking at the overall graph structure. And in link prediction, we learn the link formation in this network. So for us, we use GNNs in different hardware security systems. For example, GNN-RE, where we use the GNN to perform reverse engineering of gate-level netlists. If we look at a reverse engineered netlist, we will obtain a sea of gates, and it is difficult to identify the subcircuits that exist in this netlist, and it is difficult to understand the functionality of this design. So to get this information, we convert the netlist to a graph, and we extract a feature vector for each node in this graph. So basically, we extract features regarding the gates in the netlist, and this information will be fed to our GNN model that will tell us specifically which subcircuit each gate belongs to. So we will be able to identify the subcircuits that exist in this netlist. We'll be able to see the connections between them and figure out the design, the functionality of the design. With that, we have come to the end of our introductory video. This is the list of related publications. If you are interested, you can check out our papers and feel free to contact us if you have any questions or if you would like to know more regarding what we do.